Okay, so let's go ahead and get started. So today what I want to try and do is just finish up our discussion of Feynman diagrams. Well, perhaps not finish up, but at least take care of some of the various aspects of the perturbative expansion for quantum field theory correlation functions in terms of Feynman diagrams. So let me just begin by reminding you where we left off last class. So we're considering an interacting quantum field theory, say one whose Lagrangian is minus 1/2 times the usual kinetic term, where here I've written it by parts to make it look a little bit more symmetric, plus some interaction term. And today, I'll just focus on the case where the interaction term is just the simple phi cubed interaction that we had considered earlier. But of course, everything that I'm going to say will follow through with more complicated sets of interactions, say a phi cubed term, a phi fourth term, and so on and so forth. Okay. And the idea is that we want to compute the generating functional, which is the path integral, where we integrate over all field configurations of the classical action. So that would be the integral d4x of the Lagrangian density, plus a source term where we just by hand couple this scalar field phi to some additional quantity that we've called j, which is interpreted as a classical source for the field. And the point is that if one expands this order by order in powers of j, then this will give you the various generating functions. So, for example, the time-ordered expectation value of the field inserted at n points, x1 up to xn, is some normalization factor times a bunch of functional derivatives of this generating function with respect to j, evaluated around j is equal to 0. So the way that you're supposed to think about this is you're supposed to think about expanding, let's say you want to calculate a 2-point function, then you expand z to quadratic order in j, and the coefficient, and you'll get something that looks like integral dx, integral dy, j of x, j of y, times the 2-point function of the scalar field. And so the goal then is to develop a systematic way of computing this generating function. And the idea is very simple. The idea is that we know exactly what z looks like when we have a free theory. And so we just expand around that free theory. So you write z of j so that as well, so what is that? That's the integral d phi of e to the I integral of, say, this kinetic term, plus the source term, j phi, plus the interaction term, which was g over 6 times phi cubed. Well, we already know how to do the integral of this free theory. And you notice that taking a functional derivative with respect to j precisely just gives you an insertion of this operator phi, of the field phi, so that z of j can be rewritten as the exponential of I times this interaction term, so that was integral d4x of g times phi cubed, but we replace every phi by a variational derivative, a functional derivative with respect to j of x. Okay. So that's the interaction term. Sorry, there's a 3 factorial there. And then that is all acting on the z of j for the free theory, which is something that we computed last time. It's just the exponential. Actually, there's no I here. Sorry about that. The exponential of 1/2 of j of y, integral dy dz, j of y, j of z, times a delta of y minus z. Okay. Where delta is the free propagator. That is to say, the Feynman propagator. Okay. So is this formula more or less clear? So if so first of all, if we ignore this expression right here, then this is just the free answer that we derived yesterday, on Tuesday. And this expression that we gave for the free generating function is just Wick's theorem. It says that the endpoint function of a bunch of scalar fields is given by the sum over all ways you could pair those scalar fields together times the product of the corresponding propagators. And all we're doing here now is including this interaction term here. And the way that you could think about this is you could imagine, for example, expanding out that exponential. So in a Taylor series in G. And then you would see that the first term, the order g to the 0 term, just gives you this free result. Okay. The next term, the order g term, would have 3 powers of d by dj here. And remember, every time you take a derivative with respect to one of these j's, because of that term right there, it pulls down a phi. Okay. So then you would just get an insertion of phi cubed in the path integral, which indeed is the first order thing that you get, okay, if you expanded out this generating function at linear order in J. Just because you would be expanding e to the g over 6 times phi cubed as 1 plus g over 6 times phi cubed plus 1/2 times g over 6 times phi cubed squared, and so on and so forth. Okay. The lovely thing about this formula is that it makes it completely clear exactly how it is we can extract a perturbative expansion in terms of Feynman diagrams. Okay. So in particular, all that we do is we expand out both of these exponentials in this formula for z of j. Okay. So we'll introduce an integer that I called v, that I'll sum from 0 to infinity for that first exponential. Okay. So we get an I times g over 3 factorial times an integral d4x times the derivative with respect to j cubed of all that to the v power. And then we have the second exponential, which we express as a sum over an integer that I'll call p. And we have a 1 over p factorial, and the term appearing in the exponent. Okay, again, I think there's, for some reason, I have some various factors of I floating around in my notes which aren't correct. Of this guy, integral d4y, d4z, j of y, propagator, j of z. Okay. And then the point is that each term in this sum can be interpreted as a Feynman diagram with v vertices and p lines connecting the vertices. And the topology of the Feynman diagram tells us exactly how these various different propagators and vertices, lines and vertices, are connected together. Okay. So you can see that as you expand out the various terms in this sum, you'll get these derivatives. So you'll get some number of derivatives acting on some number of the j's here, and you'll get, so because you have a cube here, you'll need 3 j's to act on a bunch of j's here, and that means that these propagators will be connected at trivalent vertices, okay, at vertices with 3 lines coming out. And from this, you can, and when you construct the set of all possible diagrams built out of lines connected by trivalent vertices, you'll be constructing all of the possible terms in this sum that I've given for the generating function. So just to make that a little bit more explicit, so in each diagram, we will have some number of external sources. That's to say, you'll have some number of j's. So the number of external sources. So if you look at a particular term in this summation, so you have a sum over v and a sum over p. Each v has 3 derivatives with respect to j, and each p has 2 powers of j. So the total number of j's left over will be 2p minus 3v, which will be the total number of j's that are left over in a given term in this expansion. Okay. And so what we're going to do is represent in these diagrams each external source j of x by a solid dot, which will be connected to some line. And we will represent, so each vertex by a little trivalent graph like that, a dot with 3 lines coming out of it. And each propagator just by a line. And then in the Feynman rules, each one of these propagators will be each one of these lines will be a free Feynman propagator. Each vertex will give you a power of I times the coupling constant. And we will need to integrate over each power of the coupling constant, just coming from that. And we'll need to integrate over a d4x, that is to say the location of the vertex, just from this d4x here. And then each source will just be a power of j, which again will need to be integrated over. Now, at the end of the day, we're computing z of j. When you want to compute an actual correlation function, say a 2-point function, then you're going to be looking for the terms which have precisely 2 external sources, that is to say 2 powers of j, so that when you take 2 of those variational derivatives with respect to j, in this formula right here, you'll be picking out precisely the 2-point function. Okay, so let's just go ahead and write down what some of these Feynman diagrams look like. So, for example, let's start by looking at the Feynman diagrams which have no external sources. Okay. So these would just be so-called vacuum diagrams or bubble diagrams. And first of all, you see that in order for E to be equal to 0, 2p must be equal to 3v, okay? Because each propagator has 2 endpoints and each vertex connects 3 propagators. So if you don't want any external lines hanging off, then the number of propagators must be precisely 3/2 the number of vertices. And if we're working in a perturbation series where you expand order by order in the coupling G, then what you want to do is you want to start by looking at the diagrams where V is as small as possible. Okay? Those will be the ones that will be leading order in the approximation where G is very small. Okay? So you can see, because E is 0, P and V are both positive, that the smallest possible contribution, the smallest possible vacuum diagram, we'll have v is equal to 2 and p is equal to 3. That is to say you have two propagators and, two vertices and 3 propagators. And then you can just see that if you think about it, you'll see that if you have two vertices and 3 propagators, then there are precisely 2 different ways that you can construct a diagram from this. And I've drawn the 2 diagrams here. And then using these Feynman rules, you can construct a term in the expansion. And you could check explicitly, and I invite you to do so, that indeed that'll be one of the contributions to z of j up above. So for example, the term with v is equal to 2 and p is equal to 3. There are 2 different types of contribution you can get from that. There's one contribution like this, where 2 of the propagators are connected to themselves and 1 is not. And there's one type of contribution like this, where all 3 of the propagators are connected with 2 different vertices. And you can see that these correspond to the 2 different types of ways that these d by dj's can act on these j delta j terms over here. Is that clear, more or less? Okay. So don't worry, on the problems that you just picked out, you're going to work out an example of this in full, glorious detail. Where you explicitly are going to expand out this z, you're going to take a bunch of derivatives, and you're going to check that you get exactly what you would have expected from the Feynman diagram expansion. Okay. So don't worry, you'll have plenty of opportunities to check this. Okay, so let's keep enumerating these Feynman diagrams. So you might think that when v is equal to 3, you could have more diagrams, but if you think about it, if you have 3 vertices, each of which is trivalent, then you have 9 lines coming out of all of those. And propagators connect in 2 lines, and 9 is odd, so it's not a multiple of 2. So there aren't going to be any diagrams with v is equal to 2, but there are going to be diagrams with v is equal to 4, and p is equal to 6. And so let's see if we can figure them all out. So there's one right there. There's another one. There's another one. You can tell I had this worked out beforehand because you have to think a little bit, but it's not so hard. Then there's another one. Okay, and then you have the Mercedes symbol, or maybe it's a peace symbol. I don't quite remember. I guess that's a peace symbol. Okay, so those are the vacuum diagrams. So these will be the ones that are of order g squared. These will be the ones that are of order g to the 4th, and so on and so forth. When E is equal to 1, then the simplest diagrams will be those with V is equal to 1, okay, and P is equal to 2. I'm sorry, P is equal, P is equal to 1 here, okay? 3 minus 2 being equal to 1. So you'll have one external vertex, which is a j, connected to a vertex with a propagator connected to itself. The next contribution will be at v is equal to 3, and p is equal to 4, 9 minus 8 being equal to 1. And you'll have a contribution that looks like this, and another contribution that looks like this, and another contribution that looks like this. Okay. And if I have done this correctly, then those are all of the contributions that arise at order g cubed. And then you could go ahead and start working out higher order contributions at order g to the 5th. Likewise, when e is equal to 2, okay, I'm going to have to stop doing this eventually. I'll do a few more. So there's one contribution where v is equal to 0, which is just the free propagator, okay, that we know and love. There's a contribution with v is equal to 2. Okay, so actually there's two contributions. There's this one and there's this one. There will be contributions when v is equal to 4, and so on and so forth. And so, in fact, when we derived the Feynman diagrams using the Schwinger-Dyson equation, this was precisely the computation we were doing. We were computing a two-point function, and we saw that a leading order of the two-point function was the free two-point function. That's this guy here. Then there were some some higher order contributions that were of order g squared. Okay, so these are the ones that we're writing down here. And then we actually worked out even, I think, some higher order ones, or maybe we didn't, with more loops in the diagrams. Okay. So, yes, question.
Number of external sources represent the number of external points.
That's right. That's absolutely correct. So if you want to compute a Feynman diagram with n external points, then what that means you're doing is you're taking n derivatives with respect to j, which means that you need to look at the part of z which has n factors of j. Okay. Each factor of j is represented by a solid dot here. So that's what I mean by an external source. Okay. So for example, these guys here would represent a contribution to the expectation value of phi. These guys here would represent a contribution to the expectation value of phi at x1 times phi at x2, and so on and so forth. But it's sort of nice to package everything in terms of this generating function because, as you saw, this gives an extremely efficient way of packaging all of your ignorance about quantum field theory into one function. Okay. Well, it's not knowledge about quantum field theory because we don't know z exactly, but you can package everything you know into one compact expression. Okay. And then, as we're going to be doing today, we're going to start manipulating z and understanding what sort of identities it obeys. Good. Any other questions? Yes.
So the fact that ZJ is just the sum of all these diagrams, like that is why it's called the partition function, right? It's like some of the states.
Yeah, so the reason why z is called a partition function, I mean, there's a lot of different reasons why, well, okay. I mean, z, it's not just an analogy that z is a partition function. As I'm sure we'll get to at some point in this course, z is also, in a certain interpretation, literally the partition function of quantum statistical mechanics. Okay. It's not just an analogy with the partition function, it's literally the partition function. Okay. In the sense that the partition function in quantum statistical mechanics is the sum over all states of e to the minus beta e, e to the minus e over temperature. That is literally what we are computing here when we compute this partition function. Okay. There are some subtleties, though, having to do with Wick rotation, with imaginary time and boundary conditions and stuff like that. So I don't want to get into that too much right now. But this is, you know, literally the partition function of quantum statistical mechanics. Okay. I mean, if we were doing quantum mechanics, it would be the partition function of statistical quantum mechanics. In field theory, it's the partition function of statistical field theory. Good. Good question. Other questions? Okay, good. Okay, so we've used the topology of the Feynman diagram to keep track of the various different ways these lines and propagators come together. But what we really need to do is determine the numerical coefficient that goes out in front of this partition function, of this contribution to the generating function, which is what, in our previous discussion of Feynman diagrams, we call the symmetry factor. Okay. So the real question, then, is how many terms in the expansion of z of j will contribute to a given Feynman diagram. And it's only if we think about that that we can determine the numerical coefficient of each term. So, in particular, if if you look at our original expression here, you see that for a diagram with v vertices and p propagators, you get a 1 over v factorial here, you get a 1 over 3 factorial to the v power here, a 1 over p factorial here, and a 1 over 2 to the p power here. Okay? So you might think that all of those terms will appear in as a coefficient to a given Feynman diagram. But you also need to take into account the fact that when we expand out these various terms in the partition function, there are going to be many different ways that you can contract together. You can match together these derivatives with these j's to construct a given diagram. Okay. And so we just need to think a little bit about the combinatorics of this. So in particular, let's just consider a diagram with some number of vertices and some other number of propagators. Okay. So consider a diagram with p propagators and v vertices. Okay. So that comes from some term in that expansion for z. Okay. And the basic idea is that for each vertex, there are three factorial possible different ways that we could rearrange. Sorry, my handwriting is really atrocious. Possible ways that we could rearrange the functional derivatives appearing in this d by dj cubed. Okay. So for example, if you look up at this expression again, then you can see that if there's a given Feynman diagram that corresponds to a given way of matching these d by dj's with their corresponding j's, then if you choose one way of matching, you could always rearrange these 3 d by dj's here in 6 different ways, the number of permutations of 3 elements, okay? The numbers of permutations of 3 objects. And that would cancel the factor of 1 over 3 factorial right here. Likewise, for each propagator, there are 2 possible rearrangements of the j of x's in the j delta j term, which will cancel the factor of 2. So when we expand out this term right here, if you have some propagator, you could either have, if you take a bunch of derivatives that hit these 2 j's here and here, the first derivative could hit the first j, and the second could hit the second j, or vice versa. So there's 2 possible rearrangements, which cancels this 1/2 right there. Finally, you could also imagine the rearrangements of the propagators and the vertices themselves. Okay. So if you have a given contribution to this sum, where you have a bunch of vertices that are connected together to a bunch of propagators in a different way, there are v factorial ways of rearranging v vertices, which cancels that factor here, and p factorial ways of rearranging the p propagators, which cancels the p factorial right here. So the rearrangement of the vertices cancels the 1 over v factorial, and the rearrangement of the various propagators cancels the 1 over p factorial. Okay. So the total coefficient of a term, a Feynman diagram with p propagators and v vertices, will cancel. All of those v factorials, p factorials, 3 factorials, and 2's are going to cancel. Okay. Except if your diagram has some symmetries. Okay. Because this argument will overcount when, for example, a rearrangement of, say, vertices gives the same result as a rearrangement of propagators. Okay. So for certain diagrams, you will actually be overcounting, because the rearrangements of the vertices, say, that cancel this 1 over 3 factorial, may not be independent of the rearrangements of the propagators, for example. So in general, let's call a permutation of a Feynman diagram some rearrangement of the propagators, let's say of the vertices, of the propagators, of the lines coming out of the vertices, so the 3 lines coming out of a vertex, or the 2 endpoints of a vertex, and for a generic Feynman diagram with no symmetries, that Feynman diagram will not be invariant under any permutation. But the number of symmetries of a Feynman diagram is the number of permutations which happen to give the same result. That is to say, which happen to do the same thing to the diagram, which, if you think about it, is the same as the number of permutations which leave the diagram invariant. So just to say that a little bit more clearly, let's imagine that you have 2 permutations of a given diagram that happen to do the same thing to the diagram. Okay. Then you could consider the permutation 1 times the inverse of the second permutation. That would give you a third permutation that leaves the diagram unchanged. So in the argument that we gave above, we saw that every time you have 2 permutations, 2 rearrangements of the vertices, the lines, or the lines coming out of a vertex, or the 2 endpoints of a propagator, anytime you have 2 rearrangements that give you the same thing, you've overcounted by 1 the contribution of a given Feynman diagram. You can see that overcounting factor is precisely the same as the number of symmetries of the Feynman diagram under one of these permutations. Okay. So that means, because of this overcounting, that each Feynman diagram must be multiplied by 1 over the number of symmetries. Okay. So for a diagram D, then we'll call S sub D the symmetry factor, okay, which is the number of symmetries. Okay. So maybe we can do a couple examples. So we did a couple of examples last week. Let's do a few more. So let's take this diagram here. Okay. So remember, what are the allowed permutations? Well, for each vertex, you can rearrange the 3 lines coming out of the vertex. For each propagator, you can switch the 2 endpoints of the propagator. You can also permute the 2 vertices among each other, or you could permute any of the 3 propagators in this diagram among each other. Okay. So how many symmetries then does this diagram have? That is to say, how many ways are there that you have 2 different permutations that give you the same thing? Well, if you could imagine interchanging these 2 vertices, and you could do that 2 ways. You could either do that by interchanging the 2 vertices, or by exchanging the endpoints of this propagator right here. So that'll give you a factor of 2. Okay. And then you could imagine taking this propagator here and interchanging the 2 endpoints of that propagator. Okay. And that'll be the same as interchanging that line and that line, okay, which is another one of the allowed symmetries. You can rearrange the lines that come out of each vertex. So you'll get a factor of 2 from there, and then another factor of 2 from being able to do the same thing to that propagator. Is that clear, more or less? More or less? Less? More or less? Should we do another example? Okay. Let's do this example here. Okay. Often you just, often to figure out a symmetry factor, you just have to stare at the diagram long enough, and the symmetry factor will magically come to you. Okay. That's often how these things are done. That reminds me of a joke, but I'm not going to tell the joke now. Okay. So, what's the symmetry factor of this diagram? Well, there are 3 factorial, that is to say 6 different ways that we could rearrange these 3 different propagators. Okay. And we could do that rearrangement either by rearranging the p propagators or by rearranging the 3 lines that come out of each vertex. You have to do one rearrangement there and then the same rearrangement over there. Okay. So there's going to be a factor of 6 that comes from there. Okay. And then there's a symmetry that arises because you could interchange this vertex with that vertex. Okay. So that'll give you a 2. So you have 12 different symmetries of this diagram. So maybe what I'll do is next class, for my next problem set, I'll give you some opportunities to practice your chops at computing symmetry factors. Yes? Yeah, that's... I think if you think about it, that's not going to be an independent symmetry from one of the ones that we've already written down.
Is that because of the 2 factorial?
Exactly, yeah. Okay, so a lot of these symmetry factors just take a little bit of getting used to. But I hope, at the very least, the general strategy is clear. Okay. So now what I would like to do is take this Feynman diagram formalism for the computation of the generating function and understand a little bit better exactly what it is we're computing. And we'll see that, in fact, when you think about things in terms of generating functions, there are a lot of simplifications that will make our life, when we try and compute these Feynman diagrams, much simpler. So the first thing that I want to emphasize, as we've seen before, is that a general diagram is not going to be connected, but rather will be a product of some number of connected diagrams. So a general diagram is going to be disconnected, but it will be a product of a bunch of connected diagrams. Okay. So let's just think about that for a second. Okay. Let's let C denote some connected diagram. And I will be a label that labels all of the connected diagrams in the theory. The number of diagrams is countable, so I is some index that runs from 1, 2, 3, 4, so on and so forth up to infinity. And a general diagram will take the form of the product over all I of C sub I to some integer n sub I. So each connected diagram C sub I appears in a general diagram n sub I times. So that's if each Ci appears n sub I times. And there'll be some symmetry factor. So here's the clever trick. So each one of these C sub i's themselves contains a symmetry factor associated with the individual connected diagram. But there's also some overall symmetry factor associated with the fact that you could permute the individual connected diagrams among one another. Okay. And so, for example, if you have two of the same connected diagram appearing here, there are going to be 2 factorial different ways of connecting them. If you have n of a given n sub I of a given connected diagram C sub I, there'll be n I factorial ways of permuting them. So SD is going to be the product over all I of ni factorial. Okay. So let's say that your diagram is 2. So if D, say, is 2 of one type of diagram times 3 of a different type of diagram, okay, then there'll be a symmetry factor of 2 coming from here and a symmetry factor of 3 coming from here. Okay. So that means that D is the product over all I of 1 over n factorial. So the product over all I of 1 over ni factorial times Ci to the ni. Okay. Or if you want to write this out a little bit more explicitly, this means that the total partition function is the sum over all possible diagrams of D, and each diagram is labeled by a collection of integers, n0, n1, n2, and so forth. So we can write this as the sum over all integers n sub I times the product over all I, 1 over ni factorial, times Ci to the ni. Yes?
Should that be the sum over all sequences?
That's correct.
Is that what you mean by that?
That's what we mean. That's what I mean by that. Would it make you, so the sum overall, would it make you feel better if I wrote it like that? Okay. Then my goal is to make everyone feel as good as I can, humanly possible. No better. Okay. So for example, this is the sum of n0 from 0 to infinity, n1 from 0 to infinity, n2 from 0 to infinity, and so on and so forth. Okay. Now, there's nothing up my sleeve. Okay. I just want you to notice that when you have a sum of a bunch of terms times a product, you can rewrite that as the product of the sum. So it's the product over all I of the sum of n sub I from 0 to infinity, 1 over ni factorial ci to the ni. All we've done is interchange the sum and the product here. So that's the product over all I of the exponential of ci. Just performing the sum over ni. And then the product of a bunch of exponentials is the exponential of the sum. So that means that z of j is the exponential of the sum only of connected diagrams. Okay, magic. So you see that if you want to sum over all diagrams, then all you need to do is sum only over connected diagrams and exponentiate the result. Okay? This is what exponentials are good for, right? They're good at taking care of all of the combinatorics of distributing the various connected diagrams among the general diagrams. And the symmetry factors that just take into account the permutations of the individual connected diagrams in a general diagram. In fact, we already saw this last class. So for example, in a free theory, we saw that this was the exponential of 1/2 times the integral d4x d4y j of x propagator j of y, or if you want to write it in a more systematic language, the exponential of this guy. Okay. So we saw that the general partition function is the exponential of the sum of all connected diagrams. Okay. We can now use this to do something very clever. In particular, remember that whenever we compute a Feynman diagram, or whenever we compute a correlation function, what you do is you divide by z at j is equal to 0, okay, with a bunch of derivatives with respect to j acting on z. So you can now use this fact here to figure out exactly what z of 0 is. Z of 0 is just the exponential of the sum of connected diagrams with no external sources. Because if you set j is equal to 0, then you don't have any external sources. That is to say, it's the exponential of all vacuum diagrams. which we also call bubble diagrams. So in our phi cubed theory, it would be like at order g squared, you would have two terms like this. And then at order g to the fourth, you would have terms like this. And so on and so forth. So when we normalize, what we really do is compute z of j divided by z of 0. Okay. So what is that? That's the exponential of the sum of all connected diagrams divided by the exponential of the sum of all vacuum diagrams. Okay. So you can just write that as the exponential of the sum of all connected diagrams minus the sum of all vacuum diagrams. Okay, so that means that the quantity that we compute, actually, when we compute a correlation function, is not the exponential of the sum over all connected diagrams, but it's the sum over all connected diagrams without bubbles. That is to say, without a completely disconnected piece, without any completely disconnected piece, that doesn't have external lines. No external sources. Okay. So, in particular, what we've seen here is that there are no diagrams say like this, where there's just two disconnected diagrams, one of which has no external pieces whatsoever. So that means that there's a very simple rule that we can think about when we compute these Feynman diagrams, which is that we just omit all of the vacuum diagrams or bubble diagrams. And this was actually something we saw explicitly when we used the Schwinger-Dyson equation. When we computed two-point functions in the Schwinger-Dyson equation, we didn't have any vacuum diagrams contributing, but it wasn't exactly clear why, since they seemed to be allowed by the Feynman rules. And we see here that the elimination of vacuum diagrams really comes when we normalize the ground state of your theory. Because dividing by z of 0 was necessary because we needed to enforce the condition that the ground state, the vacuum state, was properly normalized. So in particular, just to reiterate, you could imagine that a diagram like this, well, it has no external sources, so it's like some contribution to the norm of the ground state. And if you normalize the ground state, then you're basically just subtracting this off. So is this clear? I mean, it's sort of remarkable that you can just manipulate, first of all, that you can think of the sum of all diagrams as the exponential of the sum of connected diagrams. And then just by normalizing it, this automatically removes all of the vacuum diagrams, all of the bubble diagrams. I mean, this is why Feynman diagrams sometimes are so useful. It's because it makes sort of combinatorial facts like this very clear. And there will be more remarkable combinatorial facts like this that appear. Okay. There'll be more in this class, even. Any questions before I continue? Okay. So far, this is all well and good. We've developed this algorithmic approach to the computation of correlation functions in quantum field theory in terms of Feynman diagrams. But there are a few details that we've been a little sloppy with, and a few things that I've brushed under the rug, which are going to turn out to be very, very important. So the first thing that I want to bring up involves these one-point functions. Okay. So what we have seen is that Feynman diagrams appear to give contributions that are non-zero to the one-point function of phi. Okay. So by translation invariance, I could always think about it at phi inserted at x equals 0. So, for example, in our phi cubed theory, there would be a contribution that looks like this, and then a bunch of higher order contributions. Okay. So in terms of the Feynman, in terms of formulas, this would be G over 2, because that diagram has a symmetry factor of 2, coming from interchanging the two, the line, the direction of the line, the two endpoints of that propagator. So, and you would get a factor of I, and then an integral d4. So let me call this x just to make things clear. So I'll insert it at a point. So you'll have an integral d4y of the propagator from x to y and the propagator from y to itself. Okay. So that's what you would get using the Feynman diagrams. And a diagram of this sort, where you just have a contribution to the one-point function, is known as a tadpole diagram. The other fun thing about Feynman diagrams is that it lets you give all sorts of fun names to formulas, okay? Because this looks a little bit like a tadpole. Okay. It had another name before it was called the tadpole diagram. You can look that up. It's a famous story. Okay. But now what I'd like to remind you of is that when we defined interacting quantum field theory several weeks ago, we noted that one can always shift phi to say phi plus a constant to set this vacuum expectation value to 0. Okay. In particular, this involved noticing that by translation invariance of the ground state, this guy had to just be a number, so it also has to be equal to the expectation value with x chosen to be a particular point. And then you could just shift phi by that number to set this equal to 0. And we decided to do this because we wanted phi to be interpreted as something which creates a particle. And this expectation value does not describe phi creating a particle. It's really phi doing nothing. Okay, it's phi acting on the vacuum, and you have a non-zero overlap with the vacuum again. So if you want to interpret phi as an operator that creates a particle, then you want to set this thing equals to 0. And you can always do that just by shifting your field phi. Okay. So what would shifting this field phi mean in terms of the Lagrangian and in terms of these Feynman diagrams? So this means that we have to insert an addition to the Lagrangian so that our Lagrangian is no longer just this phi cubed theory, but but we have to add a term that's linear in phi. Why is that? Well, because this linear term will lead to a new type of Feynman diagram. Okay, a new contribution where, in particular, a new vertex, which will allow us to cancel all of the contributions to the one-point function here coming from the Feynman diagrams. In particular, let's just imagine what would happen if we had a new interaction term, a new term in our Lagrangian that was linear in phi. Okay. So if a cubic term leads to a Feynman diagram with a vertex with three things coming out of it, this additional term will lead to a new type of vertex with one line coming out of it. So it'll look something like that. And so what we can do then is just adjust the value of y to cancel all of the Feynman diagram contributions from, say, the cubic interaction. Okay. So from the other diagrams. So in particular, so this will just be equal to I times y. So that would be the Feynman rule if you added a new vertex that only had one line coming off of it instead of three. And then what we would do is we would just choose y so that the one-point function, so you would have a contribution from the y term, and then you would have all of the contributions. Okay, I'm using a kind of sloppy notation here, where I've used an x to denote the insertion of phi of x here, and I also used an x for the y. Okay, so let's not call it y. I already used a solid dot. I don't know how to do colors on this thing. Ooh, maybe I do. Okay. Yeah, okay, let's not try and figure that out. Let's call it a box. Okay. Does that look good? That looks good. Okay. So this, you'll have one contribution to the one-point function coming from y, and then you'll have another contribution, say, coming at order g from this guy, and then another contribution at order g cubed, say, coming from this guy, and all of its other friends that contribute at order g cubed, and so on and so forth. Okay. And so this guy will contribute iy, and these guys, well, they'll contribute whatever they contribute. So they'll contribute, say, ig over 2 times, here, I guess I called this point x here, times delta xy, delta yy integrated dy, plus dot, dot, dot. Okay, plus terms that would be of order g cubed. So you can see that what we need to do in order to enforce the condition that the vacuum expectation value of phi is equal to 0 is we need to add a new term to the Lagrangian, okay, to counter the fact that we have all of these contributions to the one-point function coming from the trivalent Feynman diagrams. Okay. So we have a name for terms that we add to the Lagrangian to counter other contributions coming from your perturbation theory. We call these counter terms. Okay. And you'll learn to know, you'll get to know and love these sorts of terms. There's a sense in which the z of j equals 0 that we considered above was a counter term. Because z is the exponential of the action, so if you divide z by a constant, that's like adding a constant to the action. Okay. And that was constant we were adding was just an overall shift in, say, the energy of the ground state, okay, the energy of empty space. And so we saw we were adding that constant in order to set the energy of empty space equals to 0. Here, we're adding an interaction term, not a constant, to set the 1-point function of phi equals to 0. So in particular, we need to set this equal to 0. Okay. So that means that if you're studying these Feynman diagrams order by order in perturbation theory, then you need to evaluate this counter term y order by order in perturbation theory. So for example, at leading order, y should be equal to g over 2 times the integral delta xy, delta yy, dy, plus higher order terms. Okay. And this leads to further simplifications in our Feynman diagram expansion. Yes?
I didn't understand why the addition of y doesn't change our system.
Well, I mean, the basic point is that it will not, okay. The question is, yeah, I mean, this gets to a kind of subtle question, okay? So the point is that if you did not include y, then the 1-point function of phi would be non-zero. And we don't want that, because we want phi to be interpreted as the operator that creates a particle. And so, if you like, this is part of our definition of what we mean by an interacting quantum field theory. It's a system where you introduce terms to enforce physical constraints. Okay. And really, the idea, and this is something that will take us a little while to develop, the idea is that these counter terms are introduced. Okay, let me actually hold off on that for one more minute. But the point is that this 1-point function of phi is not actually something that you would ever observe. Okay? And so this y is introduced at an intermediate stage of the calculation in order to make your life simpler, because at the end of the day, we're going to be phrasing things only in terms of things that we can observe.
So we
Or-
could also do that, for example, cancel the contributions of the variable functions to the variable function if we want.
If you wanted to. Okay. If you wanted to. So the question is, what terms do you need to introduce in order to enforce physical principles? Okay. So what we're going to do is come up with a set of physical principles that we'll introduce that will allow us to determine, you know, what kind of counter terms we need to add to our action. Okay. So another example is that there will also be contributions to 2-point functions coming from these various Feynman diagrams. Okay. And what that means is that what we call the mass squared here will actually get corrections from these various Feynman diagrams. Okay. But at the end of the day, what do you mean by the mass? What you mean by the mass is the energy of a particle. You mean the energy of a particle with momentum k. Okay. And so if you phrase everything only, if you phrase physics in terms, if you phrase your computation in terms of the parameter m that appears in the Lagrangian, you can get answers that don't make sense. But if you phrase everything in terms of physically observable quantities, things like the energy, so where you define the mass to be the energy of a particle with momentum k, so namely the energy of a particle with 0 momentum, say the rest energy of a particle, then that will give you some sort of physical answer. So indeed, one of the other things we saw when we discussed interacting field theory is that you could rescale phi in some way. Okay. And so this rescaling of phi would allow you to adjust what m is. Okay. And so order by order in perturbation theory, what you'll need to do is you'll need to continually rescale the power factors of phi so that what you mean by mass is the energy of a particle at rest, not some random parameter that appears in the Lagrangian. Yes.
My question was if at least the classical Lagrangian,
Yes.
we have the general term.
Yes.
The classical Lagrangian.
The classical Lagrangian and the classical equations of motion change. But they change in such a way as to cancel quantum mechanical effects. Okay. Remember, this Feynman diagram expansion is a quantum it's an expansion in powers of h bar. That's explicitly clear because remember, if you go back to the beginning up here, you have a 1 over h bar here. Okay. So when you expand in powers of g, you're expanding in powers of h bar because it's e to the I action over h bar. Okay. And so what you're doing, so y is not something that appears in classical physics, but rather it's something that's of order h bar. So what you're doing is you're saying, so just to say this a little bit more clearly, you could imagine starting with a classical theory. Okay, so the equation of motion, so that's the equation of motion of a phi cubed theory. Okay, and then this is the correction term coming from that counter term. And what we're doing is we're adjusting the value of y so that when you consider the quantum mechanical contributions to this classical dynamics, it will cancel the one-point function. So we're really adjusting the Lagrangian so that the thing that actually appears, yeah, okay. Yeah, I don't know if I can say it more clearly than that. Okay. Sorry.
When we encounter the Schwinger Dyson polynomial,
Yes.
this is why when we act with the operator.
Yes, that's a great point. So yes, exactly. So for example, when you derive Feynman diagrams using the Schwinger-Dyson approach, you had the derivative of L interaction, and y would appear as a constant there. So it appears to contribute to the delta function. Right? It's the same order contribution. And it's the same order in h bar, because there's an h bar in front of that delta function. Okay. So it's an intrinsically quantum mechanical thing. It's not a classical thing. Okay, but from the point of view of the calculation of Feynman diagrams, this introduction of the parameter y, with whose value is adjusted to cancel the one-point function, makes certain things much simpler. In particular, the value of y is chosen so that whenever you have a diagram that looks like this, where you have random stuff in here, so this could be any combination of vertices and lines, this will be equal to 0, provided there are no external vertices hidden among that stuff. Okay. So even without computing it, you know that this diagram is equal to 0. Okay. Good. I didn't want to compute that diagram anyway. And in particular, because we could have any external source here, okay, we could have included any j of x here, this means that any diagram which takes the form of, say, anything, so connected to that same stuff, has to be equal to 0, provided that the stuff over here has no external vertices. Because whenever you have a diagram where you have other stuff connected to stuff with no external vertices, that's canceled by the diagram you have other stuff connected to that counter term y. You know, where you had one of these complicated diagrams. Okay. The value of y is chosen precisely so that cancels. Okay. So, if you think about it, This means that there's another simple rule that we can use to simplify our Feynman diagrams. In particular, any diagram which has the property that if you cut one line, it separates into two pieces. One of which has no external sources, then that diagram is equal to 0. So that when we think about our partition function, we really don't need to sum over all diagrams. We just need to sum over the exponential. We just need to sum over connected diagrams in the exponential. But we sum over connected diagrams with no tadpoles. That is to say, no pieces that you could cut one line and then you'll get a disconnected diagram with no sources and no vacuum bubbles. Okay. So life is getting simple. So, for example, this contribution to the 2-point function that we wrote down above, we can just forget about. Okay. That's 0 the number, not 0 some Feynman diagram. Good. Okay. Are there any questions on this? So, I just want to emphasize that we've introduced this counterterm y for physical reasons, to enforce the principle that we believe that in a sensible field theory, the 1-point function of phi should be non-zero. Okay. If the 1-point function of phi were non-zero, then that would mean that you would have some constant term appearing in the equations of motion here. Okay. That would act like a classical source for the field phi. And we want to study a field phi that's stable, that doesn't run away. So if you introduce a classical source here, then the value of field will grow and grow and grow in time. Okay. If you want to study something that's stable, then you want to study something where you have no 1-point function like this. Okay. And it turns out that the introduction of this counterterm is very important indeed. Okay. And this illustrates a general principle. So, in particular, let's ask about this term here that our counterterm is canceling. So here, I guess there I've drawn it with an external source, which is a j. I could also have an insertion of a phi there. Okay. So what is this? This is the integral d4y, delta xy, delta yy. So, what is delta yy? Well, let's just remember, so the first thing to note is that you computed delta yy on your last problem set because you computed the propagator in position space. And you saw that if you take the 2 points, you saw that if you take, say, delta xy, and you take the 2 points very close to each other, it diverges like x minus y squared. So you actually showed that for a massless particle, but it's true for a massive particle as well. So that means that delta yy is infinity. Okay. That seems to be bad, okay, because we have a Feynman diagram whose contribution is infinite. Okay. Sure is a good thing we introduced that y counter term, though, isn't it? because that y counter term precisely canceled the contribution from this term that was an infinite. Okay. So this infinity is canceled by the y counter term. Okay. So we see that that y counter term was crucially important. Because if that weren't there, then we would have all of these infinities running around in our Feynman diagrams. And this is an illustration of a very general principle, which is that when you start computing things in quantum field theory in terms of Feynman diagrams, you need to impose some physical conditions, and you need to write everything in terms of physical observable variables. But then when you translate that in terms of parameters in the Lagrangian, okay, some of those parameters will have to continually be adjusted to maintain these sort of physical conditions. And at intermediate stages in the calculations, you might appear to get infinities. But all those infinities are going to cancel out at the end of the day. So just to restate that maybe a little bit more clearly, if you'd gone ahead and started computing naively in Feynman diagram expansion in quantum field theory, you would have found that this one-point function is infinite. But we saw that that infinity can be canceled by this y counter term. And indeed, that infinity has to be canceled by this y counter term if you want to study a field theory where the one-point function of phi is equal to 0. And so this also means that, if you looked at this diagram right here, okay, you would have also expected there to be an infinity, okay, because this guy up here is also a delta y, okay, if that point right there is equal to y. Okay. So that's also infinity. But you saw that the y counter term also canceled that infinity. So the y counter term is doing a hero's work here. It's canceling an infinite number of infinities that are creeping around in our Feynman diagrams. And as we proceed and we try and actually extract physically observable quantities from these Feynman diagrams, we'll see that there are other sorts of counter terms that we need to introduce. But the general strategy, and the one that I want to emphasize, is that these infinities only appear at intermediate stages in the calculation if you phrase things in terms of unphysical quantities. If you phrase things in terms of physical quantities, everything's nice and finite. I mean, this is an idea that's going to take us a little time to wrap our heads around. We don't have to dive into it too much right now. But here, this is just our first introduction to the notion of a counter term in quantum field theory and how it plays an important role in allowing us to extract finite sensible answers at the end of the day. Okay. I'm a little over time, so maybe I'll just stop here. I'll remind you that we don't actually have class on next Tuesday, so I'll see you all next Thursday. Okay. Great, thanks.